All right, so if we continue on with this discussion of centroids, which is really going to be our focus from now on, it's going to be centroids. So the centroid being the geometric center of an object. And again, that's interchangeable in many cases we're going to deal with. Right? So in many cases we're going to deal with. So if we look at in many cases we're going to deal with, the centroid is going to be interchangeable with the center of mass. It's going to be interchangeable with the center of gravity. So if we look at the centroid in a volume, and so again, if density is constant, so if density is constant, that means the centroid is going to be the center of mass. And what we can do then is if the density is constant, I don't necessarily have to worry about the weight or the mass. I just need to worry about the volume. And so I can find the center of the volume by integrating across the entire volume, essentially, what we call the x tilde, or the location of every little differential volume, every little tiny piece of volume throughout an entire object, divided by the integral with respect to volume, dv, integral dv. So this is the total volume. So if I take the x location of every little tiny slice of the volume divided by the total volume, that will give me the x location of the centroid. And I can do the same thing. I can find the y location of the centroid by integrating the y location of every little differential volume divided by the total volume, integral dv. And the same thing for z. Z going to be integral z tilde, the location of every differential volume, the z location of every differential volume divided by the total volume. Steve, is this any more helpful? I don't know. Maybe we're getting there. Okay. We'll often encounter, this works well if I'm talking in three dimensions. What if we talk about, if we say the centroid in a volume, if the shape is constant in one dimension. Specifically, let's say that dimension is z. Right? So if the shape is constant in one dimension, I can say, well, we can say this differential volume then is equal to this constant z times dA, because it's the same. It's basically a constant z throughout, and then really I'm not so worried about the z location anymore. I'm just worried now about x and y, so I can find x bar as the integral where I take the x location of every differential area, in this case, divided by the integral dA, the total area, and I can find the y bar location. It's going to be the integral of this y location of every differential size area divided by the integral dA, the total area. Okay, and so what does this mean? Well, this means then for a function. So if I want to find the centroid of something I can describe as a function, so let's just look at x, y, and so I've got some curve that I can describe some function of x. Right, this is going to be y is equal to some function of x. Right? So what I can do then is I can say, well, you know what? I can employ this expression up here. Now, how we would apply this function up here, your text is assuming that you've not had multivariable calculus. And I'm not necessarily assuming you've had multivariable calculus either. We talked about very early on, our goal here would be to find to be able to do single variable calculus. So let's take a single variable calculus approach. Let's say that I have some differential slice of area, some dA, some differential area within this function. And so if it's a differential size area, let's say that its width then is a differential size slice x, infinitesimally small slice in the x direction. Now this is going to have its own little center, its own y tilde, and its own x tilde. That's going to be the location of the center of this little differential slice. And what we're saying here is I'm going to integrate the x bar for every little differential area, and I'm going to have a bunch of them. Talk about Riemann sum in a calculus class, right? I'm going to add up all these little differential slices, and every one of them is going to have its own x bar location. I'm going to add all those up and then divide by the total area, which is just going to be the integral of this function. And I can do the same thing in the y direction. So again, your text is going to assume that you've not had multivariable calculus. And so what it's going to do is it's going to assume that this, so we're going to treat this way. We're going to kind of basically break it down like we would a Riemann sum, so we can relate it to what you've seen in calculus, in a calculus course. We talk about integrals there. So this y tilde is going to be equal to whatever the function is at x bar divided by 2. All right, because the function at x bar, or is x tilde, it's going to be this y value here. It's going to be, it's whatever the y value at this point for x tilde is, and it's going to be halfway in between here. We're going to treat this basically like it's a rectangle, and so its center in the y direction is going to be right there in the middle. And its x bar then is just going to be this location x tilde then. And so that's location y tilde. The x tilde is just this distance here. And then dA, the differential area, is going to be the area of every one of these little differential slices. Well, the differential area is going to be whatever the y value is, whatever this y value is, multiplied by dx. Right? So again, I'm saying that the y is equal to whatever f is where I evaluated at x tilde. And again, the differential area is going to be whatever this y value is, multiplied by the width. The height times width gives me the area of this rectangle. That gives me this differential area. And so then I can substitute into these expressions here, these values. For dA, I can substitute in this. So here I've got my x bar. Then I can find as the integral where I take x, essentially the x, because remember it's x tilde dA divided by the integral dA. Well, I'm going to substitute in here for dA. I'm going to substitute in this y dA. So this is going to become this x tilde value multiplied by y dx. I'm going to substitute this in for dA. And the bottom one is just going to be the total area, because that's what the integral dA is. It's just the total area. And then realistically what you end up then just is simply, it's going to be the integral of x times y times dx divided by the total area. And that's where y is going to be whatever this function of x is. So y is going to be whatever, we're going to plug in for y, whatever this function of x. So if it's x squared, this is going to be x cubed divided by the area, or the integral of x cubed divided by the area. If this is sine of x, then this is going to be x sine x dx divided by area, whatever it might happen to be. And this is, and we're going to integrate this from, in this case, we'll say, I don't know, x at the length and x 0. So you're going to integrate it from basically 0 out to the length, the end of it. You're going to have these limits out here. We'll say this is equal to some length, and this is just 0. All right, so I'm going to integrate from 0 to L, x times whatever this function y is with respect to x divided by the area. That's a way to do it. And then if I need to integrate, if I need to find the y bar, which of course is this integral of y tilde dA divided by integral dA. And well, this is, if I substitute in here, this is y over 2 is what y tilde ends up being simplified to. So this is the integral of y over 2, halfway up the y. And I'm going to integrate and plug in here for y dx for dA. And this is going to be divided by the total area. So this just ends up being and this just ends up becoming then just this integral, again, from 0 to L. It's just going to be y squared dx over the total area. Now, this is all well and good. I don't treat it this way. This is okay. Right? This is okay. Honestly, this is how I would work these type of problems. So if I'm encountering some shape described as some function here, so let's do a little more applied. Let's say that I've got some function on the y-axis is going to come up to some maximum h, and it's going to come out to some maximum b on the x-axis. And this, again, this is some y is equal to some function of x. Okay? So I use a double integral approach. I respect if you've not had multivariable calculus. If you've not and you want to go this approach, that is perfectly fine. I think when you see how this is applied, it's really not too complicated. Excuse me, not too complicated. It sounds, Steve, a double integral. That sounds really complicated. It's really not. Let's look at it. So this is going to be, we're going to do two integrals back to back. We're going to integrate x with respect to y, and then with respect to x. And then underneath that, I'm going to integrate double integral dy dx. So what happens is dy dx, the differential y times the differential x becomes the differential area, the dA we saw up here. Right? Here I'm saying, well, if I take a single slice that's dx wide, it has a height y. Well, we're basically employing the same principle. We're just saying if I just go through this entire shape, every little differential y height, differential x width, I can integrate across the entire structure. And the limits on these integrals then is going to be from 0 to y, this function, whatever f of x is, whatever that function is, if it's x squared, if it's sine x, maybe this is e to the negative x, I don't know what it is, right? This isn't e to the negative x, but maybe some log here or something. So I'm going to go from 0 up to whatever this function is, because at any point x, it's going to go up to whatever this fx value is. And the outside integral, the x integral, is going to go from 0 out to the maximum x value is b. So on the y-axis, it's going to go from 0 down here up to whatever this y value is, whatever this fx value is. So that's the limits here. And on the x-axis, here on the outer integral, I'm integrating with respect to x. I'm going from 0 all the way out to b. So same thing here, 0 to y, 0 to b, and the same thing in the y direction. The y bar is going to be, if we do it as a double integral, if I go from the outer integral being x, so x is going to go from 0 to b, the integral integral is going to go from 0 on the bottom up to whatever this fx value is, so up to the y. So I'm going to integrate from 0 to y. For the y bar, I'm going to integrate y with respect to y, and then with respect to x. And divided by, again, integral 0 to b, integral 0 to y, dy dx. Again, if this is the first time you've seen double integrals, the good news is when you have to do double integrals later in another class, we're going to make that easier. I'm going to show you the basics. We're going to do very basic problems, and it'll be just fun. Okay. All right, so I just looked. I've got an example ready to go, but I'm looking at the time, and that's right at 15 minutes on this video. So we're going to stop there and break this up, and we'll just start an example on the next one.